Okay, so in this video, we will go over nonlinear functional forms. In the previous two, we went over just linear regressions where x and y have a linear relationship, but now we're going to go over some concepts that don't necessarily have a direct x and y linear relationship. But before we go over that, we want to recall what the definition of a slope is. And that is important because we want to distinguish what the slope is between the elasticity. Now, the slope, recall that it's the average impact of an increase in 1 unit of x on the effect of y. And so the average impact, not always consistent, just what we're estimating. And compared to slope, the elasticity measures the relation of variables in percentage terms. Keyword percentage. And so this symbol right here called eta is the elasticity symbol in Greek, and it's given by percentage change in x over the percentage change in y. And so an easy way to remember this is think of the raw change in covariance or raw measurement of covariance versus the proportional change in correlation. I think that helps. We can think of slope as a raw change versus an elasticity kind of as a proportional change. So in a way, elasticity is more useful when we're trying to measure just proportional change of how x affects y. But slope can also be helpful. It really just depends. And so for a linear regression, the elasticity is given by the b2 hat times the mean of x over the mean of y. And so using our continued example of income and food expenditure, where the slope is 10 and then our intercept is 50. Just in case if you're wondering where this 50 comes from, maybe obviously it's not going to come from our income, so you can kind of assume this 50 comes from the government or just spare money that we have outside of our salary. Okay, so we found out from the last video that our y hat will be 1050, but if we're calculating the elasticity, our beta 2 will be given by 10, and then our mean of x times the mean of y, which in our example, the income is 100 and our y value is 1050. So we'll just substitute those in. And so if you multiply 10 by 1,000, that's a little less than 1,050, so it comes out approximately 0.95. And to interpret that, we say a 1% increase in income as our x variable causes a 95% increase, or a 0.95 increase. So 1% increase in income. I'll just write that out. So 1% increase in income causes a 0.95% increase in so not a 95% increase, not like a 95 y increase, a 0.95%, so less than 1%. So just because our income increases by our food expenditure increases as income increases, but not by a direct linear relationship. Food expenditure will kind of lag a little, or it won't, not totally proportional to our increases in income. All right, so now we can get into the different functional forms. And knowing knowing how our slope and elasticity works for the different functional forms is crucial, and that because that's how we distinguish these different functional forms when we're fitting the data. And so we do that by transforming the y hat or x. We don't always have to transform the explanatory variables. We can transform the y variables like we did here. And so our first one is the linear example, which we kind of went over. But then if we go further down the road, so quadratic, cubic, we're just squaring and cubing the x's because they may potentially give a better fit or functional form than the linear relationship. Notice how they have different slopes and elasticity. If you're wondering, the slope is just measured by differentiating this part. So the 2 will go here, get rid of 2 minus 1, so the exponent is 1. This should be a 2 here. Let me just make sure that I didn't make any mistakes. Okay, there is a 2 here. So yeah, if we differentiate this part of the coefficient, then the 3 will be in front of the beta 2, and then this becomes 3 minus 1, which is 2. And then the elasticity is the same, except we're measuring the proportion, so we divide x divided by y. And then the log models, they are a little more complicated. Now, before we go into these like specific formulas, we want to know the reason why we're logging the functions in the first place. And in general, we're doing that because we want to stabilize stabilize the skewness of the data or the variance of the data. And so remember that logging a variable essentially shrinks our x or y values. I say x or y because we can also log the y value. And by shrinking it, we're shrinking because, for let's say a linear log model right here, we might want to log the x variable because in comparison to our y variable, our x variable is too big. So like for like our income and food expenditure example, our income realistically isn't going to be 100. You can't really live off an income of 100. And so when we're analyzing data sets, we want to like scale our x values or y values so that it reflects a better relationship between the x and y, or else our change or our impact might be too inflated or deflated. And then lastly, if we want to interpret the log linear and linear log in terms of like elasticity, so for the log linear, we say that a 1 unit change in x will cause 100% beta 2% change in y. And then for linear log, we say a 1% change in x will cause a beta 2 over 100 unit change in y. Mathematically, if you want to see why we get these two answers, I'm sure they're like, you can kind of go into like Google Chrome or GPT on how we get these answers or like proofs, but we just want to know why or how these, like, we can interpret these log linear log models. The log models, they're both scale, so they're not as hard to interpret, but the elasticity are definitely harder to interpret on how, these like 1 unit, 1% changes impact the dependent variable. So definitely be careful about that. So yeah, this is like a general outline of how these nonlinear functional forms can be used. And in the next video, we will go over testing these linear functions. Not like the nonlinear ones, but just linear for now. This is a more of a general overview. But in the next video, we will go over inferences.